Electricity is the invisible lifeblood of every modern building. It powers your lights, charges your phone, keeps your refrigerator running, and drives the motors in your elevator. But have you ever stopped to wonder how that raw, high-voltage electricity from the power grid gets transformed into the safe, usable power that flows through your walls? The answer lies in a piece of equipment most people never think about until something goes wrong: the distribution panel. Welcome back to the channel. In today's deep dive, we're going to explore the engineering, safety mechanisms, and practical functionality of electrical distribution panels in buildings. Whether you're a homeowner wanting to understand your breaker box, an engineering student, or just someone curious about infrastructure, this episode is for you. By the end of these 10 minutes, you'll understand exactly how electricity is distributed, protected, and managed throughout a building, and why that matters for safety, efficiency, and reliability. Let's get into it, the big picture. To understand distribution panels, we need to start with where the electricity comes from. Power plants generate electricity at high voltages, anywhere from 11,000 to 25,000 volts, sometimes much higher. This high voltage is necessary because it reduces energy loss during long-distance transmission through those massive transmission towers you see across the countryside. As this power gets closer to population centers, it passes through substations, where transformers step down the voltage to levels suitable for local distribution, typically between 4,000 and 35,000 volts. Utility companies then distribute this medium voltage power through underground cables or overhead lines to individual buildings or small groups of buildings. Here's where your building's electrical system begins. At the service entrance, usually a weatherhead on the roof or a conduit entering through the basement, electricity enters the building at what we call service voltage. For residential buildings in North America, this is typically 240 volts split phase. For commercial and industrial buildings, it's often 208 volts, three-phase, or 480 volts, three-phase, depending on the power requirements. The first component this incoming power encounters is the service entrance equipment. This includes the electric meter that tracks your consumption and, crucially, the main disconnect, a large breaker or switch that can shut off all power to the building. This main disconnect serves as the gateway between the utility's infrastructure and your building's internal electrical system. Immediately after the main disconnect, we arrive at the heart of today's discussion: the distribution panel, also commonly called the breaker panel, load center, or panel board. Think of this panel as the electrical equivalent of a train station. Power arrives on a few main lines, gets sorted, protected, and then distributed through dozens of smaller circuits to serve every outlet, light fixture, and appliance in the building. Anatomy of a distribution panel. Let's open up a typical distribution panel and examine what we find inside. Remember, in a real scenario, only qualified electricians should remove panel covers. What we're doing here is educational visualization. The first thing you'll notice is the main bus bars. These are thick strips of copper or aluminum, usually 3 or 4 bars running vertically down the center or across the top of the panel. The bus bars are the backbone of the distribution system. The incoming hot wires from the main disconnect connect to these bars, and they carry the full electrical potential of the service. In a standard North American residential panel with 240 volts split-phase service, you'll see 2 main bus bars, each carrying 120 volts relative to ground, but 240 volts relative to each other. This arrangement allows the panel to supply both 120-volt circuits for standard outlets and lights, and 240-volt circuits for heavy appliances like electric dryers, ovens, and air conditioning units. Connected to these bus bars are the circuit breakers, those rectangular switches that you've probably seen when a circuit trips and you have to reset it. Each breaker snaps onto the bus bars and draws power from them. The breakers serve 2 critical functions: protection and control. Let's talk about protection first. Circuit breakers are essentially automatic switches that monitor the current flowing through them. Under normal conditions, they remain closed and electricity flows through to the branch circuit. But if something goes wrong, say a short circuit where hot and neutral wires touch directly, or an overload where too many devices draw more current than the wires can safely handle, the breaker detects this abnormal condition and trips, cutting off power within milliseconds. Modern breakers use 2 different mechanisms for this protection. The thermal mechanism responds to sustained overloads. Inside the breaker, A bimetallic strip heats up as current passes through it. If the current exceeds the breaker's rating for a period of time, say 15 amps on a 15-amp breaker, the metal strip bends due to differential expansion, mechanically triggering the trip mechanism. This prevents wires from overheating and potentially starting fires. The magnetic mechanism responds to instantaneous short circuits. When a massive surge of current occurs, hundreds or thousands of amps, the magnetic field generated by that current pulls a solenoid plunger that instantly trips the breaker. This happens in fractions of a second before damage can occur. There's also a third type of protection found in modern panels, the arc fault circuit interrupter, or AFCI breaker. These sophisticated devices contain electronic circuitry that analyzes the electrical waveform for patterns characteristic of dangerous arcing, those sparks that can occur in damaged cords or loose connections. Arc faults are a leading cause of electrical fires, and AFCI breakers can detect these conditions and shut off power before a fire starts. Ground fault circuit interrupters, or GFCIs, serve yet another protective function. These breakers, or sometimes outlets, monitor the current flowing in the hot wire and the neutral wire. Under normal conditions, these currents should be equal. If the GFCI detects even a tiny imbalance, as small as 4 to 6 milliamps, it assumes that current is leaking somewhere it shouldn't, possibly through a person to ground, and trips immediately. This protects against electrocution. Beyond the breakers and bus bars, you'll find the neutral bar, usually a terminal strip with multiple screws where all the white neutral wires from the branch circuits connect. The neutral bar is electrically isolated from the metal panel enclosure, but connects to the main neutral wire returning to the utility. In main panels, the neutral bar is also bonded to the ground bar and the panel case. The ground bar, often green or bare copper, provides a safety path for fault currents. All the bare copper or green grounding wires from the circuits connect here. If a hot wire ever touches a metal electrical box or appliance frame, the ground wire provides a low-resistance path that causes the breaker to trip immediately, rather than leaving the metal surface energized and dangerous. Finally, we have the panel enclosure itself. A metal box that contains all these components provides protection against accidental contact with live parts and serves as the grounding electrode for the system. How power flows through the system. Now that we understand the components, let's trace the complete path of electricity through a distribution panel and see how it serves a typical circuit. Power enters from the utility through the service entrance conductors, heavy-gauge wires, typically 20 or 30 AWG aluminum, or 10 or 20 AWG copper for residential services. These connect to the main lugs, or the main breaker in the panel. From the main connection, current flows into the bus bars. Imagine these as the electrical equivalent of a highway. Now, each circuit breaker connects to this highway like an on-ramp. When you install a 20-amp breaker for a kitchen outlet circuit, you're essentially creating a controlled exit ramp from that electrical highway. The breaker connects to the hot bus bar through its back panel connection. When the breaker is switched on, current can flow through the breaker's internal mechanism, out through the load terminal, and into the black hot wire of the branch circuit. This wire runs through the walls to serve multiple outlets or fixtures in what we call a home run, the path from panel to the first outlet, then daisy-chained to subsequent devices. At each outlet or light, the hot wire connects to the device. When you plug something in or flip a light switch, you complete the circuit. Current flows through the device, doing work, heating a coil, spinning a motor, or illuminating a filament, and then returns through the neutral wire. All the neutral wires from the various branch circuits return to the panel and connect to the neutral bar. From there, the main neutral conductor carries the combined return current back to the utility transformer, completing the circuit. In a properly balanced system, the current in the neutral wire is the difference between the currents on the two hot legs, not the sum. For 240-volt circuits, like those serving electric ranges or air conditioners, the setup is slightly different. These double-pole breakers connect to both hot bus bars simultaneously, capturing the full 240 volts between them. The appliance uses both hot wires and often doesn't even need a neutral connection, since the load is balanced between the two phases. The grounding system operates somewhat differently. Ground wires don't normally carry current. They're there purely for safety. Each outlet box, switch box, and appliance frame connects to the ground wire, which returns to the panel's ground bar. The ground bar connects to the neutral bar at one point, the main bonding jumper, and also to the building's grounding electrode system. This grounding electrode system might include metal water pipes, ground rods driven into the earth, or concrete-encased electrodes. Its purpose is to maintain the earth and the building's electrical system at the same potential, and to provide a path for lightning or fault currents to dissipate safely into the ground. When everything works correctly, you never notice this system. But when something goes wrong, say a wire insulation fails and touches a metal box, the ground wire provides an immediate, low-resistance path for fault current. This current surge is large enough to trip the breaker instantly, de-energizing the fault before someone can touch the electrified surface. Safety, maintenance, and modern innovations. Understanding distribution panels isn't just academic, it has real safety implications. Electrical fires cause hundreds of deaths and thousands of injuries annually, and many of these tragedies stem from panel issues. One common problem is overloading. As we add more devices to our lives, computers, entertainment systems, electric vehicle chargers, older panels become undersized. When a panel is consistently loaded near its capacity, breakers wear out, connections loosen from thermal cycling, and fire risks increase. If your panel is warm to the touch, makes buzzing sounds, or has breakers that trip frequently, these are warning signs requiring professional evaluation. Another issue is outdated equipment. Panels installed before the 1990s may lack modern safety features. Some older panels, particularly certain brands from the 1960s through 1980s, have known design flaws that create fire hazards. If you have an older home, having an electrician inspect your panel is a wise investment. Proper labeling is also crucial for safety. Every breaker should clearly indicate what it controls. Kitchen outlets, master bedroom, HVAC unit. In an emergency, being able to quickly shut off the right circuit can prevent injuries or equipment damage. Many panels come with pre-printed labels, but these should be verified and customized during installation. Modern innovations are transforming distribution panels. Smart panels, equipped with internet connectivity and energy monitoring, can track consumption by circuit in real time. You can see exactly how much your air conditioner costs to run, receive alerts when circuits approach overload, or remotely shut off power to specific areas. Some smart panels integrate with home automation systems and can shed loads automatically during peak rate periods to save money. Others work with solar panels and battery storage, managing bidirectional power flow and ensuring critical circuits stay energized during outages. Arc fault and ground fault protection continue to evolve. Combination AFCI breakers now protect against both series arcs, like those in damaged cords, and parallel arcs, like those between hot and neutral wires. These devices have become mandatory for most residential circuits under recent electrical codes, significantly reducing fire risks. Surge protection is another growing feature. While point-of-use surge protectors at outlets help, whole-panel surge protective devices installed at the main panel can stop surges from entering the building's wiring in the first place. These are becoming standard in areas with frequent lightning or utility switching transients. Until next time, stay curious about the systems that surround you, and remember, every time you flip a switch and the light comes on, there's a distribution panel somewhere making that moment possible, safely and reliably. Take care, and I'll see you in the next video.